We're beginning chapter 13. Chapter 13 deals with conic sections, and in this chapter we have 4 sections. We will be covering all 4 sections of chapter 13. Of course, on this video we only are concerned with section 13.1, that is conic sections, parabolas, and circles. Or those are the 2 conic sections we are interested in. So here are the exercises that we're going to go over. Some of them, the ones in highlighted, are the ones for your homework. And there's also another piece. There you go. There's more down here, number 55. So let's begin with actually section 13.1. In section 13.1, the beginning of the discussion here, the conic sections. So what are conic sections? The conic sections are actually, these are the sections. The reference to section here is a section of the cone that you're looking at. So here what I have is, let me show you how these cones are generated. If you look at this line here, this line that I called it a generator, if we rotate this line about the vertical axis, which would be the axis of symmetry of the cone here, so about the vertical axis, if we rotate this generator, and I do have it here in a better drawing. So imagine this is the generator that was in the other sketch, and if this generator begins to revolve or rotate about some vertical axis of rotation at some angle of rotation, then the result's going to be a cone that's created up here and another cone that's generated down below. Imagine this top portion of this generator as it revolves. It creates, I'm looking at from this point upward, it generates the upper nap of the cone. Again, these are called, the cones are called double napped cones. So this would be the upper nap, and this is the lower nap of the cone. And this is how these cones are generated. These 2 cones are generated. Now, once we have the cones generated, suppose a flat surface crosses the double napped cone at various angles relative to the generator. So here's a case, for example, the flat surface crosses the upper nap of a cone, and the impression that it leaves, that flat surface leaves or makes on the upper nap of the cone, in this case seems to be a parabola. And if the flat surface crosses it, the upper nap of a cone parallel to the base of the cone, then we get what we call a circle. So these are all down below, down here. These are the 2-dimensional reflection of what you see up here on the cone. Again, the surface here crosses the upper nap at an angle such that it generates the ellipse. And finally, if the flat surface crosses both naps of the cone, then we get a branch up here and another branch down here, and the result is what we call a hyperbola. Now, these conic sections were discovered by Apollonius of Perga around 1300 years ago. So they're pretty dated. However, the use of these conic sections even today are used quite often in a lot of different applications, most of which involve telescope designs and lens designs, and also a lot of interesting ideas as far as the reflections in the mirrors go, and the mirror designs. Actually, all of these involve conic sections. A good example would be the satellite dishes that you probably see all over the place. These satellite dishes are mostly parabolic satellite dishes. So it has a wide range of applications even today. So our work is to study the equation of these conic sections. Now, each of these shapes that you see here, the hyperbola, ellipse, circle, and the parabola, each of these have what we call the degenerate cases. So, for example, the degenerate case of the parabola is going to be a line. That's as the parabola approaches the apex of the lower nap. And both circle and the ellipse, both of those degenerate to a single point. Okay. So again, both circle and ellipse degenerate to a single point as the circle moves closer, as it falls closer to this point here where the two naps meet. The circle becomes a point, so does the ellipse. The hyperbolas, as you move closer to the intersection of the two cones, they degenerate to two crossing lines. One of them goes this way, the other one goes in this direction. Now, we are not going to work with degenerate cases. In this section and the sections that follow, we are interested in the equation of these conic sections. That's the extent of what we're interested in. So let's begin with the parabola. Now, we've already discussed parabolas, I believe, was it chapter 11 maybe? We discussed parabolas extensively. Those parabolas were primarily vertical parabolas. That means those were the parabolas that were in this form, the polynomial form of the parabola that we've seen before. Now, in this section, we're also going to look at the other kind of parabolas. These are the sideways parabolas. This one, where you have x equals ay squared plus by plus c. Notice in this form, by the way, we have switched the role of x and y. So we interchange x and y, and this is what we're going to get. So turn all your x's into y's and turn your y into x. So indeed, what we've done by switching x and y, we're looking at the inverse of that equation. And that is the parabola that we talked about earlier. The inverse of this parabola is going to be the one below it. When y is 0, in this case, for the horizontal parabolas, and by horizontal, we're talking about the axis of symmetry of the parabola being horizontal. So if you let y be 0, you can immediately see that x would equal to c, which suggests c is the x-intercept. Remember the point where y would be 0, that is the x-intercept of the graph. So I'm just going to write that here. It's going to be c comma 0, and that's going to be the x-intercept of the horizontal parabolas. So let's continue on. Now, what you're seeing here, what you're looking at, and I've highlighted for you, and this is the HK form of the parabola. Just remember, we've seen HKs before. So this is the HK form of, this time, the horizontal parabola. Again, we've switched x and y precisely. Now, because we switch x and y, then if you remember the coordinates of vertex for the vertical parabolas were at HK, where h was negative b over 2a. In the case of horizontal parabolas, actually the vertex here, let me see if I have that. No, let me write it. So the vertex here is actually going to be at negative b over 2a. And I'm just going to write x here, and then to find the x, to find this x, the x component of the vertex, you simply plug in negative b over 2a in the equation. In the equation of the parabola. That's how we do it. I cannot do f at negative b over 2a because, as you will see in a moment, these horizontal parabolas are not functions, so we cannot use function notations with them. So let's take a look at our first example. First example is on page 854, exercise number 30. In this exercise, we have x is equal to negative y squared, negative 2y plus 3. And we would like to graph this parabola. So just like before, I'm going to identify the ABCs here. Remember, a is a number that multiplies by the squared. So a is going to be negative 1. A would be something that multiplies by y squared. B is the coefficient on y, and c is the constant by itself. So here are my ABCs. Now again, the vertex is going to be at x and negative b over 2a. So I did negative b over 2a here. Hopefully you can follow. And I get negative 1. Now to find the x component of the vertex, we're going to plug it into the equation. And when we plug into the equation, so here's negative 1 plugged in, and you work the arithmetic of this, and I got 4. So the coordinates of the vertex are going to be 4, negative 1. And that will give us a point on the graph of the parabola. Now, a, the number that we found up here, a is -1. If a is negative, means less than 0, if a is negative, this horizontal parabola is going to open to the left. And if a is positive, it will open to the right. So this parabola is going to open to the left. Now, a point on a parabola here is going to be when y is 0. I just picked a random point here. And I like to let y be 0 because when y is 0, you plug in here, you get 0. Up here, you get 0. 0 and 0 plus 3 makes 3. I don't need a calculator for that. So x becomes 3. And there we have it. The point on the parabola is going to be 3, 0. So let me show you now how the parabola is actually graphed. Remember, we found the vertex to be this point. It's going to be 4, -1. So that's the coordinates of the vertex. And it's right up here. So this is 4 and -1. That's the vertex. One point on the graph of this parabola was 3, 0, right? The x-intercept. And remember, we need 3 points. Definitely vertex. And we need 1 point on either side, either branch of the parabola. So once I got this 3, 0, the way I found this point is by reflection about this horizontal axis of symmetry. Okay, and that's what I did. So here's 3, 0, and the reflection of that will be down here. So I got my 3 points, and let's say I graphed it by drawing this curve through these 3 points. Of course, I use a software, so it looks more professional. And there you have it. So this is how we're going to graph these horizontal parabolas. So remember, you need the vertex, and then the x-intercept, and the reflection of x-intercept. That will give you the 3 points we need. Now let's take a look at this one. Exercise number 24. X is equal to y squared plus 3y. So for this one, again, you can see the ABCs are A is 1, B is 3, and there is no constant here, plus minus nothing here, so C is 0. Because A is 1, A is positive, so we know that this parabola is going to open to the right. And what I need to do is I need to find the coordinates of the vertex, and the y component of the vertex is -b over 2a. So I plugged in -b here. That's b is 3 divided by 2a, and that gave me -3/2. We then plug in this y -3/2 up here for y and up here for y. And when we do, you follow the arithmetic of this one, and of course it involves fractions, but once we plug them in, -3/2 squared, well, 3 squared, 2 squared makes 9/4. 3 times -3/2 makes -9/2. And I do need a common denominator, right? The LCD is 4, so I have to build this fraction. Multiply its denominator by 2, its numerator by 2, and that gave me the 9 minus 18/4, or -9/4. And there we have that one. So now we have the coordinates of the vertex, -9/4, -3/2, and I went ahead and graphed this one. So that's our one important point. A must point to have is the vertex. So here's the vertex. And remember, this thing is going to open to the right because A was positive. Now my other point here, again, remember, we would like to stay with the x-intercept. The x-intercept is the C part, where C is 0 here. Or you can just make y 0, y 0. You can see x would be 0. Therefore, 0, 0 is where the x-intercept is. And this point is actually 0, 0 on the graph is right here. That's 0, 0. That's this point right in here. Okay, and let me make it readable. Okay, so how do I get this second point? Remember, I use reflection about the axis of symmetry, which is this line. In this case, the y component is -3/2. So this is at -3/2. Okay, that's where this line is. Actually needs to be a little bit higher. I know that doesn't look, it needs to be more right up here. So this would be actually the axis of symmetry will be this one. So I'll just, there you go, bold it, and it will make it go through that. But nevertheless, that is our axis of symmetry, which is halfway between -1 and 2. That's -1.5. But anyhow, the reflection of 0, 0 down to the point below it, right in here, that gives me my third point. And then you can draw a curve that runs through these 3 points. And that will give me the actual graph of this parabola. Now, one thing I mentioned is that vertical line test that I mentioned. So if you look at it here, this is what I meant. See, when I do a vertical line test, it crosses the graph at more than 1 point, which tells me the sideways parabolas are not functions. So anything we do with functions, you cannot do with these parabolas. Okay. And let's get rid of this now. All right, and so we're done with this graph. Now, next we're going to take a look at circles. Now, here's actually how a circle is created. That's, again, when a flat surface crosses a nap, either the upper or the lower nap of the cone, parallel to the base of the cone, right here. So that's how you get this circle on the outside. And then the circle here has a center at HK. So we are allowing for center of the circle to be away from 0, 0. So in this particular one, it's at HK. And the equation of the circle is x minus h squared plus y minus k squared equals r squared. Now, r here is the radius of the circle. Okay. And the derivation of this formula, by the way, is in your book. You're welcome to look at it if you're interested. So the center of this circle, again, is going to be at HK. Now, notice the r here is in a squared form. So a number in a squared form, the base is what the radius is. So we'll see how we can find the radius in a general equation using an example. Now, this is the equation of that circle that we see up here and highlighted. It's just written down here now. The parameters of the circle, we need the center and the radius. Okay. Now, and this is actually the graph of two different circles that you're looking at. The one in blue is a circle that's centered at 0, 0. So h and k are 0 respectively in this one. R is the radius. So this would be, again, a circle at 0, 0 centered. And this other one is actually a circle that's allowed to be off center. I mean, off the origin. It doesn't have to be centered at the origin. Okay. And let's take a look at an example here. So this example is exercise number 36 in your book. And in this example, they want us to find the equation of a circle whose center is at 5, 6, and the radius is 11, square root of 11 actually. So for this one, I have the equation. Again, remember that we got the equation directly from earlier, and it's right up here still. See, that's the equation of the circle with any center. So I'm just going to plug in 5 for h and 6 for k, and r was the square root of 11. So plug in all those numbers into the general equation, and you can see that we get the equation of a circle to be what you're looking at. Now notice in here, by the way, the right side is 11. That 11 is r squared. And what was saying earlier is the base of this r squared. R is the radius. So if you're given a number 11 that is not radius, in order to find the radius, we actually take the square root of this number, and that's what's going to give us the radius to be square root of 11. Now, for the graph, in order to graph it, I'll show you how I graph it without plotting points. We don't want to go plotting points here. Now, square root of 11 is about 3.3-ish, right? So here's how I actually graph this circle. I started from the center. Remember the center here. The center was at 5 and 6, right in here. Now, square root of 11 is about 3, a little over 3. So at this point, I move to the right 3.3 units. I go to the left 3.3. You then go up north 3.3, and then you go south 3.3. So you move in all four directions. You go east, west, north, south. Same distance. The distance is 3.3. And then you just draw the best circle you can through these four boundary points. And that's how we're going to graph our circles. That's how we're going to draw them. So you don't need to plot points. So like, let's say, for example, when x is 0, y is this. When x is 1, y is that, and so on. Notice also the graph of the equation of a circle does not represent a function. So you can see again, it fails the vertical line test. If I just draw, a line here, right in there. You see that line crosses the circle at 2 points. Anywhere along the circle, I move this line. There you go, over here. Again, it's crossing it at 2 different points. So that just goes to show me that the graph is not a function. So again, the implication of that is that the things we can do that we're allowed to do with functions, we cannot do with these. Let's take a look at exercise number 50. In exercise number 50, we are given the equation of a circle. And initially, actually, there's no r squared here. So this one, the equation was x plus 5 squared plus y minus 1 squared equals 15. That's what that was. I just on my own went ahead and wrote that equal r squared, so to reinforce the fact that the number is r squared. It is not r, but r squared. So for this one, we actually want to find the center and the radius because it is in the hk form. So h here is going to be -5 and k is going to be -1. Remember, h is not 5 here, it's -5. We've been through that before. It's -5 because we gotta have a negative in the form. The form is x minus, right? X minus h squared. So your positive 5, we can write it as double negative. So it's gonna be like negative of -5, right? That's gonna be a positive 5. So this is actually what the h is. H is -5. Okay, just want to point that out. It's always opposite of what it seems to be inside parentheses. You see, that's a positive 5. H is actually opposite of that. Here, -1. K would be opposite of that, which is a positive 1. Now, r squared is 15, so to find the radius, we take the square root of the number, whatever the number might be. Now, square root of 15, I know it's not 4. I'm saying it's just about 4 because the way I graph them. It's going to be like 3.8. So almost 4. So here's how I actually graphed this circle. So I started with the center at -5 and 1. And then I went almost 4 units to the right, almost 4 to the left, up and down. And then I drew the circle through those 4 points. Notice again, I'm not plotting points. Okay, that's not how we want to do that. So let me just to mention what I mean. Plotting points would be this, like if I have x, y, you go -2, -1, 0, 1, 2, and whatever. There you go. We don't want to do that. Okay, we do not want to plot points. Let's take a look at this one. Now, this equation, interestingly, number 56, we don't have the hk form. The reason it's easy to graph these circles, if they're in the hk form, they're pretty simple to graph. You just find the center, you have the radius, you go equal distance to the right, left, north, south, and you draw the circle. So what if we don't have the hk form? Well, the case where we don't have the hk form, what we do is we actually complete the square. Now, completing the square method, I have the details here. Remember how this method worked. The coefficient on x squared has to be a 1 and y squared has to be a 1 before we start, and both of them are. So our next step is to get half of the coefficient on x, in this case 6, half of 6, and then don't forget we square it. Once we square it, half of 6 is 3, 3 squared makes 9, and here you go, this is 9. The next one, y squared negative 4y half of negative 4 is negative 2. You square, you get 4. So I'm going to add 9 in the first expression. I'm going to add 4 in that second expression. Now, anything we do to the left, we do to the right of an equation to maintain the equilibrium or the balance of the equation. So 9 and 4 makes 13 on the left, 9 and 4 makes 13 to the right, and so this is balanced. Now on the right side, I combined 13 and 15, got 28. Remember, that is r squared. And then in exchange, because I have a perfect square trinomial here, I'm going to rewrite x squared plus 6x plus 9 as x plus 3 squared. Y squared negative 4y plus 4, that becomes y minus 2 squared. And there we have it. Now this is now the HK form. And remember, opposite of this number. So h is going to be what? Negative 3. And k, opposite of this number, opposite of negative 2, is going to be 2. And of course, I use color here to show you that h is the colored numbers. Or actually, no, sorry, h is not the color number. I use color because just to show you what was added to create a perfect square trinomial. I use red here, green here, because there are two different expressions. Now, to find the radius, we take a square root of 28. So the exact radius is actually going to be 2 root 7. Right, that's simplifying the radical. And if I want to actually graph it, I need to know approximately how much that is. Square root of 7 times 2, if I did it right, I got about 5.3. So this time I'm going to go to the right, to the left, north, south, 5 units to draw my circle. And I did. Once I have the center of the circle, remember the center is at negative 3 and 2. So I started at the center, negative 3, 2. Then I went to the right about 5. Again, I know it's 5.3 here, but I just want to show you approximately 5 units to the right is what I went. These are not going to be actually points on the circle. If you want to make them exact correct points on the circle, then we could actually correct them. And let's see, for this one, because it's 5.3, so from the center, which was, what you call it, 3 units to the left, you go 5.3, negative 3 plus 5.3, that's going to be, there you go, plus 5.3, that makes it 2.3. So that's what that point is. I'm just writing approximately how I did this. Went to right 5, left 5, up 5, down 5. So you can actually make these exact values. And once you have them, then you can draw the circle, and that will complete our circle this way. Number 58, I think this is our last problem we're going to look at. Just another one like the one we did, one that's not in standard form. So we do need to complete the square in this one also. And first step, I group the x's together, the y's together, and just like the one above, we do the same thing. It just so happens it's almost the same expression. Move 12 to the right side, so that made it negative 12. And then combine 4 and 9, that made 13 to the right. Now, how did the 9 and 4 come about? There you go. Half of the coefficient on x, half of 6. That would be 3 squared 9. That's this number. Half of 4 is 2. 2 squared is 4, and that is this number. So I'm going to exchange this trinomial in exchange for square of a binomial, x plus 3 squared, and this we exchange this one with y plus 2 squared. Negative 12 plus 13 makes 1, and here's the HK form of the circle. Now, next step, I actually want to show you exactly the HK form. So what I'm doing is I'm using the x minus, here's your h, y minus, and here's your k. So h is negative 3 and k is negative 2. And those are the coordinates of the center. The radius, remember, will be square root of this number. Square root of 1 remains 1, so you're not going to see a change there. And this is the graph. And so how did I do this again? We started with the center at -3, -2, then went to the right, 1 left, north 1, south 1, and I drew the circle through those boundaries. And that's all there is in this section. So keep in mind, in order to graph the circle, we need to have the circle in standard form, the HK form. Otherwise, it's not going to be as easily drawn. And we do not want to plot points with this one. We just want to use the general form to do it. And we talked about the sideways parabolas, and with that we are done with this section 13.1.